Welcome to part 2 of our lesson on substitution and elimination reactions. In this part of the lesson, we will turn our attention to elimination reactions. We'll begin with an overview of elimination reactions in general, discussing the fundamental principles and why these reactions are important in organic chemistry. Following this, we'll look into the mechanistic details of the reaction and learn about the E2 and E1 pathways. We'll explore each of these mechanisms in detail, the conditions under which they occur, and their key differences, looking at several examples along the way. A significant part of this lesson will be dedicated to predicting reactivity. We'll compare substitution and elimination reactions to help you understand the factors that determine whether a molecule will undergo substitution or elimination. This comparison will be crucial in mastering the prediction of reaction outcomes based on differences in the substrate and conditions being utilized. By the end of this part of the lesson, you should have a clear understanding of both substitution and elimination reactions, including how to identify when they will occur and how to draw the structures of the products that will form. Let's go ahead and get started. Elimination reactions are fundamental in organic chemistry, often serving as the counterpart to addition reactions. While addition reactions involve adding atoms or groups to a molecule, elimination reactions remove atoms or groups, leading to the formation of a double bond. When this occurs in an alkyl halide substrate, an alkene is the product of the reaction. This is a key reason why eliminations are important to us. They provide us a tool for the preparation of a valuable functional group that we can use in chemical synthesis. One important consideration we need to keep in mind is that elimination reactions can compete with substitution reactions. This competition is because both types of reactions have very similar starting materials, reagents, and conditions. For example, both substitution and elimination reactions require a good leaving group on the substrate. If a reagent can act as both a nucleophile and a base, which we will see is quite common, we frequently see eliminations occurring alongside substitutions in a single reaction environment, and a mixture of products results. This competition can significantly impact the yield of the desired product. Let's look at elimination reactions in more detail. There are two main mechanisms by which eliminations of alkyl halides occur: E2 and E1. E2, or bimolecular elimination, involves the simultaneous removal of a proton and a leaving group, with the reaction rate depending on the concentration of both the substrate and the base. E1, or unimolecular elimination, involves a two-step process where the leaving group departs first, forming a carbocation intermediate, followed by the removal of a proton. We need to learn about both mechanisms in order to understand how elimination reactions occur. We will start with E2 eliminations on the next slide. After that, we will look at the E1 mechanism. Let's start with a detailed explanation of the E2 elimination mechanism, a fundamental concept in organic chemistry. The E2 mechanism, which stands for bimolecular elimination, involves a single concerted step, where all bond-making and breaking occur simultaneously. In this process, a strong base abstracts a hydrogen atom from the beta carbon. Recall that the beta carbon is the carbon directly adjacent to the one bonded to the leaving group, which we call the alpha carbon. This removal of the beta proton causes the electrons in the bond to flow into a new pi bond between the alpha and beta carbons, while the leaving group departs with the electrons that were in the covalent bond it shared with the alpha carbon. In the diagram, the base, represented by the letter B, attacks the hydrogen atom on the beta carbon. The curved arrows illustrate the movement of electrons. One arrow shows the electrons from the base attacking the hydrogen atom. Another shows the electrons from the carbon-hydrogen bond moving to form the pi bond between the alpha and beta carbons. A third arrow indicates the departure of the leaving group with its bonding electrons. This simultaneous action, where bond breaking and bond formation occur at the same time, characterizes the concerted nature of the E2 mechanism. The transition state in this mechanism is crucial to understand. It represents a high-energy state where bonds are partially formed and broken. In this transition state, we see two molecules, the base and the substrate. The presence of these two molecules together in the transition state is why the reaction is termed bimolecular, and it significantly impacts the reaction's kinetics. To get this reaction to happen, both of these species need to be present. Another idea to think about is that if a reaction mixture contains a reagent that is highly reactive, like a strong base, that species will tend to interact with the substrate, forcing bimolecular reactions like this one. Because the transition state involves both the base and the substrate, the rate of the reaction depends on the concentration of both. The rate equation for the E2 reaction reflects this, as the rate is directly proportional to the concentrations of both reactants. Several conditions favor the E2 mechanism. For example, a strong base is necessary to effectively remove the hydrogen atom from the beta carbon. This is because the base needs to be strong enough to overcome the energy barrier for this deprotonation step. Without a strong base, such as hydroxide or alkoxide, it is less likely that the E2 pathway will occur. Additionally, the presence of good leaving groups, especially when they are on more hindered or sterically crowded positions such as tertiary or secondary carbons, enhances the E2 reaction. A good leaving group can stabilize the negative charge once it departs, making the elimination process more favorable. When the leaving group is on a sterically hindered position, a nucleophile is not able to form a bond to the alpha carbon because it is shielded by the various substituents. Instead, it is more likely for the reagent to encounter a beta proton and undergo the elimination reaction. The presence of at least one beta hydrogen atom is also essential. Without a hydrogen atom adjacent to the carbon with the leaving group, the elimination process cannot occur. If the substrate has a leaving group attached to a primary carbon, a more sterically hindered base is required for elimination to take place. A small base can easily reach the alpha carbon and favor a substitution reaction over elimination. Using a bulky base ensures that the substitution pathway is minimized or avoided, thus promoting the E2 elimination. Now that we have covered the fundamental aspects of the E2 reaction mechanism, let's move on to the next part of the lesson. We will focus on predicting the structures of the products that can form, and determining which of those products should be favored by this mechanism. As we saw on the previous page, in an E2 elimination reaction, a strong base deprotonates a substrate at the beta position, resulting in the simultaneous removal of the leaving group and the formation of a double bond. Consider the substrate in the diagram below. The name for this compound is 2-bromo-2-methylbutane, and notice that by inspecting the structure of this compound, we find that there are several beta positions. This begs the question, if multiple types of beta protons are present, which one do we remove in the elimination reaction? It turns out that the base can remove any of the beta protons. This means that if there are multiple beta positions, an E2 elimination can produce a different alkene for each one. This is because in the E2 reaction, the pi bond forms between the alpha and beta carbon atoms. Therefore, our first step in drawing the products of the E2 reaction is to analyze the substrate with the goal of locating all of the beta positions. Here is an outline of the process. We will try this out on several examples that follow. First, identify the alpha carbon. This is the carbon that is directly bonded to the halogen atom. The alpha carbon is the starting point of your analysis. Next, locate the beta carbons. Beta carbons are the carbons that are directly bonded to the alpha carbon. Each beta carbon is a potential site for deprotonation during the E2 elimination process. Next, examine the molecule structure to identify equivalent beta carbons. Equivalent beta carbons are in identical environments due to the molecule's symmetry. Label each beta carbon with the Greek symbol for beta, followed by a numerical subscript. For example, beta 1, beta 2. Assign the same subscript to equivalent beta carbons. Distinct beta carbons receive different subscripts. Equivalent beta carbons produce the same product upon elimination, and are counted as a single unique beta position, sharing the same label. Let's consider a practical example. Take 2-bromo-2-methylbutane. In this molecule, the alpha carbon is the carbon bonded to the bromine. The beta carbons are the carbons adjacent to this alpha carbon. We can label them all with the Greek symbol beta. Now we must determine which positions are equivalent, and which are unique. Notice that the two methyl groups are interchangeable. Elimination from either methyl group would produce the same alkene, so we can label these both as beta 1, since they only represent, collectively, one unique beta position on the molecule. The other beta position, however, is distinct, and elimination from that position would result in the formation of a different alkene. We can label this carbon as beta 2. Because the substrate has two distinct beta positions, beta 1 and beta 2, E2 elimination results in the formation of two different products, as is shown in the reaction scheme below. The first structure is the product formed by removal of the proton from beta 2, and the second product is formed when the proton from beta 1 is removed. Notice that these two products are not formed in a similar amount. The favored product, by far, is the one resulting from the elimination from beta 2. Notice that these compounds are isomers. They have the same formula, but are structurally different from one another. These types of isomers are known as regioisomers, and the preference for forming one regioisomer over another is called regioselectivity. Regioisomers are a specific type of isomers that differ in the position of substituents attached to the main carbon chain in organic molecules. These isomers have the same molecular formula and the same functional groups, but the connectivity of the atoms differs in such a way that the functional groups are located at different positions on the carbon chain. For instance, in the case of alkenes, regioisomers can arise from different placements of double bonds or from the attachment of substituents at different carbons within the chain. To summarize, these two alkenes are regioisomers, and the elimination reaction shown here favors the formation of one of these regioisomers over the other. The regioisomer with the more substituted alkene is favored over the less substituted alkene. To communicate this idea more concisely, the more substituted alkene is referred to as the Zaitsev product, while the less substituted alkene is known as the Hofmann product, named after the organic chemists who conducted early research in this area. Understanding the preference for forming the Zaitsev, or Hofmann product, is crucial in predicting the outcome of E2 reactions. So, what factors influence this selectivity? To answer this, we need to explore the stability of alkenes, which leads us to our next topic. When predicting the products of E2 elimination, alkene stability is a key factor. The stability of an alkene is related to the degree of substitution at the carbon-carbon double bond. Alkyl groups stabilize the double bond through a phenomenon known as hyperconjugation, where the electron density from the alkyl groups delocalizes into the pi bond. So the more alkyl groups attach to the alkene carbons, the more stable the alkene. To determine the substitution of an alkene, you need to carefully examine the carbon atoms involved in the double bond. First, identify the carbon-carbon double bond within the alkene. Next, look at each carbon atom in the double bond, and count the number of substituents attached to it. Substituents can be hydrogen atoms, alkyl groups, or other functional groups. For each carbon in the double bond, count how many of these substituents are not hydrogen atoms. For example, the first structure on the right has one alkyl group attached to one of the carbon atoms of the C-C double bond. This is a monosubstituted alkene. In the second example, there is one alkyl group attached to each of the carbon atoms of the C equals C double bond, making it a disubstituted alkene. A trisubstituted alkene is shown next, as it has 3 alkyl groups attached. And finally, we see a tetrasubstituted alkene, which has 4 alkyl groups attached. Notice that these groups are listed from left to right, in order of their increasing stability. This has a direct impact on the regioselectivity of E2 eliminations. The stability of the alkene increases with the number of alkyl groups attached to the double bond. Recall that the so-called Zaitsev product, which is the product with the more substituted alkene, is favored in E2 eliminations. This is due to the greater thermodynamic stability of the Zaitsev product compared to the Hofmann product. Before we practice with some examples, we have one additional concept to review: the stereoselectivity of E2 eliminations. We will cover that on the next page. In addition to the degree of substitution, the geometric configuration of alkenes also affects their stability. As we have seen, cis isomers are generally less stable than trans isomers, due to steric strain. The bulky groups on the same side of the double bond in cis isomers cause more repulsion compared to trans isomers, where the bulky groups are on opposite sides. For this reason, E2 elimination reactions will generally favor the formation of the more stable trans isomer. There are cases in which the cis isomer is produced as the major product, but this topic is reserved for the next course in this series. To summarize, E2 eliminations will favor the formation of the more stable alkene product, when more than one is possible. The selectivity of the reaction for the formation of the more substituted alkene is referred to as Zaitsev's rule. Using this idea, that these reactions show regioselectivity for the more substituted alkene, we can predict the location for the new pi bond in the structures of our products. Furthermore, we can also predict the stereochemistry of the alkenes that are formed in E2 eliminations. Because the trans isomers have less steric strain than cis, the trans isomers are often the favored product in stereoselective E2 eliminations. Now that we have covered the key concepts of E2 eliminations, including regioselectivity and alkene stability, we are equipped to apply this knowledge to predict the products of various E2 reactions. Let's move forward with some examples and further applications to solidify our understanding. Let's go through each of the following examples of E2 eliminations together, step by step, and understand the process of identifying unique beta positions, labeling them, and drawing the different regioisomer products. We will also determine which product is the major one and why. Feel free to pause the video at any point and attempt the examples yourself as practice. In the first example, we have 2-bromopentane as the substrate, reacting with sodium ethoxide. Sodium ethoxide is a strong base. Its conjugate acid is ethanol, which has a pKa of approximately 15. As a base, sodium ethoxide works well in E2 eliminations of alkyl halides. Our analysis starts by identifying the alpha carbon, which is the carbon bonded to the bromine atom. Next, we locate the beta carbons, which are the carbons adjacent to the alpha carbon. In this molecule, there are 2 distinct beta carbons. One beta carbon is on the left side of the alpha carbon, and the other beta carbon is on the right side. We can label these as beta 1 and beta 2. When elimination occurs from beta 1, we form 1-pentene. When elimination occurs from beta 2, we form 2-pentene. These are the 2 possible regioisomers formed in this reaction. The more substituted alkene, which is 2-pentene, is known as the Zaitsev product, and is favored because it is more stable. Therefore, 2-pentene is the major product, and 1-pentene is the minor product. In the second example, we have 2-bromo-2-methylpentane reacting with sodium methoxide. Sodium methoxide acts as a strong base in this reaction. Here, the alpha carbon is bonded to the bromine atom. We locate the beta carbons next. There are two distinct beta carbons in this molecule. One beta carbon, beta 1, is part of the main carbon chain, while the other beta carbon, beta 2, are the methyl groups. For the purposes of product formation, we only need to consider one of the beta 2 carbons, because they are chemically equivalent in this reaction. Elimination from beta 2 produces 2-methyl-1-pentene, which is the Hofmann product. Elimination from beta 1 produces 2-methyl-2-pentene, which is the Zaitsev product. The more substituted alkene, 2-methyl-2-pentene, is favored due to its greater stability, and is the major product. In the third example, we have 1-bromo-1-methylcyclohexane, reacting with sodium methoxide. Again, sodium methoxide serves as a strong base. The alpha carbon is bonded to the bromine atom. There are 3 total beta carbon atoms in this structure, and we identify them by locating the carbon atoms directly connected to the alpha carbon. Notice that because of symmetry, the 2 beta carbons within the ring are equivalent, and we can label them as beta 1. The other beta carbon is the methyl group attached to the alpha carbon. We can label this as beta 2. The Zaitsev product, which is the major product, is formed by elimination from beta 1, and the Hofmann product from beta 2. In the fourth example, we have a bromo-substituted naphthalene derivative, reacting with sodium methoxide. Sodium methoxide acts as a strong base. The alpha carbon here is bonded to the bromine atom. We locate the beta carbons next. There are 2 distinct beta carbons in this molecule, each located in a different ring of the naphthalene structure. Due to symmetry, we can assign the beta 1 labels to 2 of the beta positions, as shown here. The third carbon atom attached to the alpha carbon is labeled as beta 2. Elimination from either of the beta 1 carbons leads to the minor product, which is the less substituted alkene. This is also called the Hofmann product. Elimination from the beta 2 carbon leads to the formation of the major product, because it is the more substituted alkene. This is the Zaitsev product. Now that we have solidified our understanding of the E2 elimination, let's go to the next page and start learning about the other possible mechanism, the E1 reaction. Recall that E1 eliminations, like SN1 reactions, are a stepwise process. Another similarity they share is that E1 reactions, like SN1 reactions, involve the formation of a carbocation intermediate, as the rate-determining step in the mechanism. Consider the example transformation below, which proceeds by an E1 mechanism. In the first step we see a loss of leaving group occur, as the bromine departs with the electrons in the covalent bond. This results in the formation of a carbocation intermediate, and a bromide anion. Next, a beta hydrogen is removed. This is a proton transfer step. The electrons that were shared with hydrogen now go to form a pi bond, resulting in the elimination product. Typically, E1 reactions occur under conditions that involve a tertiary substrate in an alcohol solvent. As is shown in the above example, the E1 process begins with the loss of the leaving group, resulting in the formation of a carbocation intermediate. This intermediate is then followed by the elimination of a beta hydrogen, facilitated by the solvent, to form the final alkene product. Because the SN1 and E1 mechanisms have the same mechanism, in the first step, these reactions often accompany one another. Let's see how that works on the next page. Both E1 and SN1 reactions diverge from a common intermediate, which is generated in the first step of both mechanisms. As a consequence of this, reactions that proceed by an E1 mechanism are often accompanied by SN1 products, and vice versa. On the slide, you can see an energy diagram illustrating this process. Initially, the substrate loses the leaving group to form the carbocation intermediate. From this point, the reaction can proceed in one of 2 ways, either by elimination to form an alkene, which is the E1 pathway, or by nucleophilic substitution to form a different product, which is the SN1 pathway. Because both pathways proceed from the same intermediate, it is common to obtain mixtures of SN1 and E1 products in a reaction. The exact ratio of products can vary depending on several factors, including the nature of the substrate and the reaction conditions. Understanding this shared mechanism helps us understand the limitations of these reactions and prepare accordingly. Let's go to the next page and look at some example E1 reactions. Let's now look at some specific examples of E1 elimination reactions. There are a few key characteristics that all of these reactions share, which make them favor the E1 mechanism over E2 or SN2 mechanisms. As we work through these examples, see if you notice those patterns. In the first example, we identify the substrate alkyl halide by the presence of the bromine atom attached to a tertiary carbon. The presence of a tertiary carbon, where the leaving group is attached, is crucial because it makes it possible to form a relatively stable carbocation intermediate once the leaving group departs. Furthermore, the use of ethanol, a polar protic solvent, stabilizes the carbocation. Notice the absence of any strong bases or strong nucleophiles. Without a strongly reactive reagent, it is unlikely that a bimolecular reaction would occur, simply because there isn't a second molecule to participate in the reaction. What this means is that these conditions disfavor the SN2 and E2 reactions because of the lack of a strong nucleophile or strong base. They do, however, favor unimolecular reactions. We would expect to see an E1 elimination, producing the Zaitsev alkene, along with SN1 product, in which the solvent, ethanol, replaces the leaving group. It isn't important to try and predict which one is major or minor, but it is important to know that both can form. Notice I did not include the Hofmann product. That was intentional, as Hofmann elimination products are not generally observed when E1 conditions are used. Next, we have a reaction involving a tertiary alcohol with concentrated sulfuric acid and heat. In this example, the alcohol undergoes protonation by the strong acid, converting the hydroxyl group into a good leaving group, water. This leads to the formation of a carbocation intermediate. The tertiary carbon structure, combined with the stabilizing effect of the polar protic environment and the use of heat, make the E1 reaction favorable. Notice that there is no nucleophilic solvent present, like methanol or ethanol, to act as the nucleophile here, so substitution products from an SN1 reaction aren't formed. Finally, consider the example reaction of the alcohol shown here, when subjected to concentrated sulfuric acid and heat. Similar to the previous example, the alcohol is protonated, turning the hydroxyl group into a good leaving group. The reaction proceeds through the formation of a stable carbocation intermediate. Again, the tertiary structure of the carbon, holding the leaving group, along with the polar protic solvent and heat, supports the E1 mechanism. The product generated would be the most thermodynamically stable alkene, which would place the two phenyl rings on opposite sides of the double bond. Notice that because the alkene is trigonal planar, the molecule is drawn flat, without any wedges or dashes. These example reactions share some common features that we should note. 1. Tertiary carbon centers. Notice that each substrate has a tertiary carbon where the leaving group is attached, allowing for the formation of a relatively stable carbocation intermediate. 2. Polar protic solvents. The solvents used, such as ethanol or concentrated sulfuric acid, help to stabilize the carbocation intermediate. The use of polar protic solvents helps promote E1 and SN1 mechanisms. 3. Heat. Though not always shown in the reaction equation, the application of heat helps to drive the elimination process, favoring the formation of the double bond. 4. Formation of a stable carbocation. The key step in all E1 reactions is the formation of a stable carbocation intermediate, which then undergoes elimination to form the final alkene product. These factors combined make the E1 mechanism more favorable than the E2 or SN2 mechanisms in these examples. The E2 mechanism typically requires a strong base and a less hindered substrate, while the SN2 mechanism is hindered by steric effects and does not proceed well with tertiary carbons. Note that we also see some E1 reactions accompanied by SN1 reactions, as long as a suitable solvent like methanol, ethanol, or water is present. Before we move on from E1 reactions, we should also look at an example mechanism. Let's go to the next page and see one of the more interesting uses of E1 reactions, and see if we can draw the mechanism. One of the most common uses of E1 reactions is in the deprotection of tert-butyl ethers. Protecting groups are essential tools in organic synthesis, used to temporarily mask a functional group to prevent it from reacting under certain conditions. In the context of alcohols, a protecting group like a tert-butyl ether can be used to shield the hydroxyl group during a reaction, allowing other parts of the molecule to react without interference. Once the desired transformations are complete, the protecting group is removed to regenerate the original alcohol. Let's walk through the mechanism of this reaction step by step. We start with tert-butyl propyl ether, reacting with concentrated sulfuric acid and heat. The reaction proceeds through an E1 elimination mechanism to produce isobutene and propanol. First, let's consider why we need to protonate the ether. Ethers are generally stable compounds with poor leaving groups. In order to initiate the reaction, we need to convert the ether into a more reactive species. Sulfuric acid, being a strong acid, donates a proton to the oxygen atom in the ether. This protonation converts the oxygen into an oxonium ion, making it a better leaving group. The protonated ether now looks like this. The oxygen is bonded to a hydrogen, resulting in a positively charged species. Next, the protonated ether undergoes cleavage. The bond between the oxygen and the tert-butyl group breaks, resulting in the formation of a tert-butyl carbocation and a propanol molecule. This step is crucial as it forms the carbocation intermediate, which is a hallmark of the E1 mechanism. Now we have a stable tert-butyl carbocation. This intermediate is highly favored because it is a tertiary carbocation, which is more stable than primary or secondary carbocations, due to inductive effects and hyperconjugation. The final step is the elimination of a proton from the carbocation to form the alkene. A base, which is typically the conjugate base of sulfuric acid, abstracts a proton from one of the methyl groups adjacent to the positively charged carbon. This results in the formation of a double bond, producing isobutene. In summary, the reaction proceeds as follows. The ether is protonated by sulfuric acid to convert it into a better leaving group. This protonation step is crucial to make the ether reactive. The protonated ether then undergoes cleavage, leading to the formation of a tert-butyl carbocation and propanol. The carbocation then undergoes elimination to form isobutene. This E1 mechanism involves the formation of a stable carbocation intermediate, and the subsequent elimination of a proton to form the final products, isobutene and propanol. Through this step-by-step mechanism, we see how the reaction conditions favor the E1 pathway, leading to the formation of an alcohol and an alkene from the original ether. Now that we've discussed the individual mechanisms of SN1, SN2, E1 and E2 reactions, let's move on to an important skill in organic chemistry: predicting reactivity. Even though substitution and elimination reactions are almost always in competition with each other, we can generally predict the major and minor products based on the reaction conditions provided. When trying to determine if an alkyl halide will undergo substitution or elimination, and by which specific mechanism, it is always helpful to start by remembering that there are only 4 pathways to consider: SN1, SN2, E1, and E2. When you are presented with a substrate, reagents, and conditions, your task will be to A. Determine which reaction or reactions will likely occur, and B. Draw the corresponding products for those reactions, indicating which, if any, are favored as the major product. To accomplish this task, I strongly suggest using the method I am outlining here. I think of this method as a type of process of elimination, where we analyze the information we are given, and from that information, rule out as many of the 4 mechanism types as possible. Here's how it works. First, you are going to analyze the substrate. You want to focus your attention on the alpha carbon, classifying it as primary, secondary, or tertiary. From this information, you now try to eliminate any of the 4 pathways, specifically those that are impossible based on the substrate structure. For example, a primary alkyl halide is unlikely to undergo an SN1 or E1 reaction due to the instability of the resulting carbocation. So if you are confronted with a primary alkyl halide, the only 2 reactions that are possible, of the 4 being considered, are the SN2 and E2 reactions. Next, your task is to determine the role of the reagent. Remember that the reagents are the compounds written above and below the reaction arrow. The goal here is to determine what that reagent can do in the reaction. Reagents might act as strong bases or strong nucleophiles, or they might be both at the same time. Other roles you might see are weak nucleophiles, such as solvents like water, methanol and ethanol, and acid catalysts like sulfuric acid. To determine the role of the reagent, ask yourself questions such as, is this a strong or a weak base? And, is this a strong nucleophile or a weak nucleophile? To help answer these questions, remember that strong bases have conjugate acids with a pKa greater than 10. If the conjugate acid has a pKa of 10 or below, it is not a strong base. Strong nucleophiles are often negatively charged. Neutral oxygen atoms, for example, are not strong nucleophiles. An exception to this is sulfur. Whether neutral or negative, sulfur is always an excellent nucleophile, unless it is bonded to oxygen or other electronegative atoms. Strong bases favor elimination reactions, particularly E2. Examples of strong bases include hydroxide, alkoxide, amide, and acetylide ions. Weak bases, on the other hand, such as halides, acetate, thiolates, and water, often favor substitution reactions, particularly SN1 and SN2. Additionally, it is crucial to remember that multiple products from different mechanisms are possible. For instance, under certain conditions, both substitution and elimination products can form, and the conditions will determine which product is major and which is minor. By following these guidelines, one can predict the reactivity and outcome of given reactions. The specific conditions and the nature of the substrate and reagents will guide us to the most likely reaction pathway. Let's look at some examples and practice predicting the outcomes of reactions based on these principles. This will help solidify our understanding of how to apply these concepts. For each of the example reactions below, I am going to apply the same strategy that was outlined on the previous page to identify which of the 4 reaction types is likely to occur. From there, I will use my understanding of the reaction type to draw the products that would be expected, highlighting any selectivity for one regioisomer or stereoisomer over another. Let's see how this works on the first example. Your analysis should start by locating the alpha carbon and classifying it by degree of substitution. The alpha carbon is the carbon directly bonded to the leaving group, which in this example is a bromine atom. Because the alpha carbon is bonded to 3 other carbon atoms, it is classified as tertiary. Now that we have established the substrate substitution, we can try to eliminate some of the reaction pathways. Can you remember which of the reaction pathways is impossible with a tertiary alkyl halide? That's right. The SN2 pathway is incredibly slow to occur on tertiary alkyl halides due to steric hindrance. As a result, we can cross this pathway off the list of possible reaction mechanisms. The next step for us is to turn our attention to determining the role of the reagent. In this example, we see that the reagent is potassium tert butoxide, whose structure has a negatively charged oxygen atom that is directly connected to the tertiary carbon atom of the tert butyl group. Based on this information, we can identify two main features of this reagent. First, it is what we can call a strong reagent. The formal negative charge on oxygen indicates that it is highly electron-rich, and so is ready and able to react. Because we have established that the reagent is not weak, we know that the reagent is going to participate in the reaction mechanism. This means that the reaction is not likely to undergo any of the unimolecular reactions, so we can cross out the E1 and SN1 reactions from our list. Notice that the only reaction left remaining is the E2 reaction, and that will be the pathway that occurs in this reaction. The conjugate acid of tert butoxide is the alcohol called tert butanol. Like other alcohols, it has a pKa somewhere around 15. This means that tert butoxide is a strong base. Remember, when the conjugate acid pKa is greater than 10, the compound in question is a strong base. The other notable feature of tert butoxide is that it is very sterically hindered at the reactive oxygen. This steric hindrance limits tert butoxide's ability to act as a nucleophile on secondary and tertiary substrates, because there would be significant repulsive forces preventing the oxygen from reaching the alpha carbon when the substrate is also sterically hindered. What all of this means is that our reagent is a strong base and a very sterically hindered nucleophile. We already know that the only remaining pathway is the E2 reaction, and so now it is time to draw the product, or products, if more than one is possible. For E2 eliminations, we need to locate each unique beta carbon. On this substrate, we see there are two distinct beta positions, which have been labeled as beta 1 and beta 2. Notice that the methyl groups are indistinguishable, and so both are labeled as beta 2. Because there are two distinct beta positions, that means there are two possible products. We can draw each of these by drawing the pi bond that forms during the elimination between the alpha and beta carbon atoms. The product formed by elimination from beta 1 is the more substituted alkene, and is called the Zaitsev product. The product formed by elimination from beta 2 is the less substituted alkene, and is called the Hofmann product. This example highlights an interesting feature of E2 reactions that we will discuss in more detail in the next course in this series. Specifically, while the Zaitsev product is usually the favored major product, when a very bulky base like tert butoxide is used, it is possible to form the Hofmann product as the major regioisomer. The reason is not difficult to understand, if you consider that the steric hindrance around the base causes it to be more selective to react with the least hindered part of the substrate. Let's move on to the second example. Our analysis begins by identifying the alkyl halide substitution as primary. Because the alpha carbon only has one alkyl group attached, this means that its ability to form a carbocation by loss of the bromide leaving group is severely limited due to the very high energy of primary carbocations. This means we can eliminate reaction pathways that require the formation of a carbocation. So we can cross out both the SN1 and E1 reaction pathways based on the structure of the substrate, leaving behind just SN2 and E2. Looking at the reagent, we see potassium tert butoxide again. As we discussed in example 1, tert butoxide is a strong base and a sterically hindered nucleophile. Because it can act as both a base and a nucleophile, we have to consider the possibility that both the E2 and SN2 reactions are possible. Let's draw the structure for both products. The structure of the substitution product simply replaces the carbon halide bond with the tert butyl ether bond. To determine the elimination product, we identify the beta carbon atoms on the substrate. We see there is only one beta carbon in this example, and so there is only one possible alkene that would form in the elimination reaction. In order to know which of these two products is favored as the major product, we would need to look into experimental evidence, as there is nothing definitive in the mechanism or other theory we have discussed that would tell us this answer. Fortunately, this experiment has been performed and documented. When a primary alkyl halide reacts with potassium tert butoxide, the reaction will favor the elimination product. The reaction shown here gives a yield of 85% for the elimination product, compared with 15% for the substitution product. We can generalize this result and assume that in reactions of primary alkyl halides, bulky bases like tert butoxide will favor E2 over SN2, though both will form. Let's move on to the third example. Here we see a primary alkyl bromide reacting with sodium hydroxide. We start our analysis by noting again that primary alkyl halides will not undergo SN1 or E1 reactions due to the instability of primary carbocations. We can then look at the reagent to see if we can determine if substitution by SN2 or elimination E2 is favored for this reaction. To do this, we try to determine if the reagent, sodium hydroxide, can act as a base, a nucleophile, or both. For basicity, we can consider the pKa of hydroxide's conjugate acid, which is water. Water has a pKa of 15.7, which is greater than our suggested cutoff value of 10. This means that hydroxide can act as a strong base. Nucleophiles are species that are strongly attracted to electron-deficient atoms. This means that nucleophiles usually are electron-rich, which we can identify by noting the presence of non-bonding electron pairs on an atom, a negative formal charge, or the presence of pi bonds. The oxygen atom in hydroxide has a formal negative charge due to the presence of 3 non-bonding electron pairs. This indicates that hydroxide would be a strong nucleophile, and it will be highly reactive towards electrophiles. Additionally, the small size of the hydroxide ion allows it to easily approach and attack electrophilic centers in molecules, facilitating nucleophilic substitution reactions. This high reactivity enables hydroxide ions to effectively displace leaving groups and form new bonds in nucleophilic substitution reactions. To summarize, hydroxide is both a strong nucleophile and a strong base. This means it is capable of participating in both substitution and elimination reactions. Let's draw the products for these two pathways. To draw the substitution product, we replace the bromide leaving group with the hydroxide on the alpha carbon. To draw the elimination product, we remove the leaving group and draw a pi bond between the alpha and beta carbon atoms. Let's discuss which of these two products will be favored in the reaction. In the previous example, we saw that primary alkyl halides react with bulky bases to give E2 and SN2 products as well, and that the major product was found to be from the elimination reaction. This is due to the steric bulk of the base preventing significant amounts of substitution from occurring. In this example, we do not have a bulky base. Hydroxide is small, and as mentioned, this means it can easily access the alpha carbon and perform the substitution reaction. For this reason, the substitution product is favored as the major product. Let's go to the fourth example. Here we see a secondary alkyl halide reacting with sodium hydrosulfide. Secondary alkyl halides do not have the same limitations as primary and tertiary alkyl halides. They can undergo unimolecular reactions that require the formation of a carbocation, and they are not so sterically hindered to prevent substitution reactions from taking place. For this reason, we cannot eliminate any of the 4 pathways based on the substrate structure. Let's see if we can learn more by considering the reagent. Sodium hydrosulfide is the sulfur analog of hydroxide, meaning if you replace the oxygen atom in hydroxide with a sulfur atom, you will have hydrosulfide. The sulfur atom, like oxygen, has 3 non-bonding electron pairs, and thus carries a negative formal charge. This means it is also very electron-rich, and we should consider it to be a strong nucleophile. Sulfur is larger and more polarizable than oxygen, meaning that the electron density around the sulfur atom is more diffuse. This diffuse electron cloud allows the anion to be highly reactive towards electrophiles. When a hydrosulfide ion encounters an electrophilic center, it readily donates its electrons to form a new bond, making it an effective nucleophile in many organic synthesis reactions. So we know that it is a strong nucleophile, but is it also basic, like hydroxide? To answer that question, we can consider the pKa of its conjugate acid, which is hydrogen sulfide, or H2S. This compound has a pKa of approximately 6.9. Our simplified pKa table rounds this up to 10. This means that the anion, hydrosulfide, with the formula HS-, is not a strong base, as its conjugate acid has a pKa of 10 or below. So if hydrosulfide is a strong nucleophile, but not a strong base, what should be the outcome of this reaction? Because hydrosulfide is a strong reagent due to its strength as a nucleophile, we know that it will be involved in the reaction mechanism, which means it favors bimolecular reactions like SN2 and E2, and disfavors unimolecular reactions like SN1 and E1. With only SN2 and E2 remaining as viable pathways, we then have to consider if the reagent is a nucleophile, a base, or both. Nucleophiles favor substitution, bases favor elimination, and species that are both nucleophiles and bases can react both ways. We determined that hydrosulfide is a good nucleophile, but a poor base. This means we can cross out E2 as a viable reaction pathway. We have determined that the product formed in this reaction will be from an SN2 reaction. Let's see how to draw the structure of that product. To draw the structure, we need to replace the leaving group with the nucleophile at the alpha carbon. To do this, we attach the sulfur atom of HS to the alpha carbon. We also need to remember that the chirality will be inverted at chiral carbon atoms undergoing SN2 reactions. We can show this by changing the wedge bond to a dash bond, which indicates that it has inverted its configuration. With the information shown in these 4 examples, you are ready to try the next 3 examples on your own. After I conclude the lesson in a moment, the answers, along with notes on how these were determined, will be displayed. You should continue your practice of this skill using the assigned homework, and then assess your understanding again with the lesson quiz. This brings us to the conclusion of Lesson 6. We have covered a lot of ground in this lesson, and you now have many tools at your disposal to interpret, predict, and conduct organic reactions. I look forward to seeing you again in the next lesson. Thanks for watching.